Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at trigonometry made somewhat easier. So, in this topic we're going to start with a background. Why trig? We're going to give a geometric interpretation of the trigonometric functions. We will then use the Pythagorean theorem to derive many of the results you saw in secondary school, and a few more, and we will then use similar triangles to derive others. To begin, why trig? Well, first of all, engineering is all about the transfer of energy and information. Water wheels in ancient days were used to convert potential energy to create rotational motion. And if you were in a sawmill, it was sometimes necessary to convert that rotational motion back into linear motion. An internal combustion engine uses a piston to convert linear motion back into rotational motion. Sound is a combination of frequencies which is then interpreted by your ear. Sound synthesis therefore requires the combination of outputs of numerous oscillators, all at various frequencies. Alternating current, the power you get when you plug something into a wall outlet, is sinusoidal. Alternating current is actually very superior to direct current, which is what you get out of a battery, as transformers can step up the voltage of AC and therefore reduce the current, and consequently this reduces power loss during transmission in high voltage transmission lines. Sensors like radar are also cyclical in nature, and so all of these can be modeled by trigonometric functions. Now, given an angle theta, let us create a line that makes that angle theta between that line and the positive x-axis. Let's extend that line from the origin with that given angle. That line at some point is going to intersect the unit circle. The length of that line from the origin to that point of intersection must be equal to 1, by definition. Now, from that intersection, drop a line down to the x-axis. Now, the part of the Roman toga that hung down from the left shoulder was called the sinus. We will define the length of this line dropped down to the x-axis to be a length equal to sine theta. From that intersection point, we can also draw a line to the y-axis, and this axis completes a rectangle, or completes the coordinate. We will define the length of this line to be cosine of theta. That is, it is the complementary sine of the angle theta. Now, from the intersection line, we can draw a line that is tangent to the unit circle at that point until that line intersects the x-axis. That line is 90 degrees to the original line which we drew from the origin with angle theta. We will therefore define the length of this line to be tan theta, or tangent of theta. Now, remember that a tangent line is a line that touches a curve at a single point. Also, from that point of intersection on the unit circle, we can extend the line until it intersects the y-axis. This line completes the tangent line, and therefore we will define the length of this line to be the complementary tangent or cotangent of theta. Next, consider the length of the line along the x-axis from the origin up until the intersection of that tangent line. We will define the length of that line to be secant of theta. Now, recall that a secant line intersects a curve at 2 points, unlike a tangent line which intersects only which only touches a curve at a single point. Similarly, consider the length of the line that follows the y-axis from the origin until the intersection of that tangent line. We will define that length to be cosecant of theta. That is, it is the complementary secant, and it is the line that completes the triangle together with the secant line. Now, first of all, let's recall the Pythagorean theorem that says that if we have a right-angled triangle with sides of length A and B adjacent to the right angled, then the length of the hypotenuse C is related to A and B through the formula A squared plus B squared is equal to C squared. To prove this, let's make 3 additional copies of this triangle and lay them out as we see here. In this case, this forms a square with sides length A plus B. Now, also from the properties of angles within a triangle, we also see that the interior angles within this shape must also be 90 degrees. Thus, the interior must also be a square, and because each of the sides of that square is the hypotenuse, the area of that interior must be equal to C squared. Now, therefore, C squared is equal to the area of the entire square, which is A plus B all squared, minus the area of the 4 triangles. Each of those triangles has area 1/2 base times height, or in this case, 1/2 AB, and as there are 4 of them, we will subtract off 4 times that area. This produces A squared plus 2AB plus B squared minus 2AB. The 2 terms cancel out, leaving us with A squared plus B squared. Also, as a consequence, as everything is positive, C must be equal to the square root of A squared plus B squared. Now, to apply the Pythagorean theorem, we require a right-angled triangle. Well, actually, we have 6 such triangles. Let's look at each of them and see the consequential deduction we may make using the Pythagorean theorem. So here we see our first right-angled triangle with sides sine of theta, cosine of theta, and 1. Consequently, sine theta squared plus cosine of theta squared is equal to 1 squared, which is equal to 1. Here's another triangle where one of the sides has length 1, another side adjacent to the right angle is tan theta, and the hypotenuse is secant theta. Therefore, tan of theta squared plus 1 squared, which is 1, equals secant of theta squared. Now here's another triangle. Again, the sides adjacent to the right angle have length 1 and cotan of theta, and the hypotenuse is cosecant of theta. Therefore, consequently, 1 squared plus cotan of theta squared is equal to cosecant of theta squared. And here we have a fourth very large right-angled triangle. Again, the sides adjacent to the right angle are secant theta and cosecant theta, and the hypotenuse is cotan theta plus tan theta. Consequently, Pythagoras tells us that cosecant theta squared plus secant theta squared is equal to tan of theta plus cotan all squared. Here's a cute little triangle. The two sides adjacent to the right angle are secant minus cosine, and the other side is sine, whereas the hypotenuse is tan. Therefore, secant theta minus cosine of theta all squared plus sine of theta squared must equal tan of theta squared. And here's its matching sixth right-angled triangle with sides cosine theta, cosecant theta minus sine of theta, and cotan of theta as the hypotenuse. And so therefore cos of theta squared plus cosecant theta minus sine theta all squared must equal cotangent of theta squared. So now we've finished applying the Pythagorean theorem to get 6 formulas. Now we're going to carry on with similar triangles. Two triangles, as seen below, are said to be similar if all of their angles are the same. And what this means is that the ratios of corresponding sides must also be equal. So for example, the ratio of the length A over the length B must equal the ratio D over E in the second triangle. Similarly, the ratio A over C must equal the ratio D over F, and finally, the ratio of C over B must equal the ratio F over E. So as long as you have two triangles that are similar, then the corresponding ratios of the lengths of the sides must also be equal. Well, we have 6 right-angled triangles here, all of which have a right angle, one angle theta, and therefore the third angle must be 90 degrees minus theta. Thus, all 6 of these triangles must be similar. Therefore, let's take the ratio of the sides adjacent to the right angle. Looking at the first triangle, we get sine over cosine. Looking at the second triangle, we get tangent over 1. Looking at the third one, we get 1 over cotangent. And in each case, notice that at least for these 6 triangles, the numerator is always the shorter of the two lengths. In the fourth triangle, we have secant theta over cosecant theta. Here we have sec theta minus cosine theta all over sine theta. And finally, in the last image, we have cosine theta over cosecant theta minus sine theta. So all of these ratios must be equal. The most important takeaways from here, however, is that tan theta equals sine over cos, but also equivalently, it is also equal to secant over cosecant. Cotangent is cosine over sine, or cosecant over secant. And finally, we get the familiar formula that tan theta is the reciprocal of cotangent of theta. Next, let's take the ratio of the sides adjacent to the angle theta. We will always have the shorter length in the numerator and the length of the hypotenuse in the denominator. So in the first case, we have cosine theta over 1. And this ratio must equal 1 over secant theta in the second image. In the third image, this must equal cotan theta over cosecant theta, which in the fourth image must equal cosecant theta over cotan plus tan. In the fifth image, we have sine over tan of theta, and you should see that this is true because tan is sine over cos. So if we divide sine by the ratio sine over cosine, the signs cancel and we're left with cosine in the numerator. In the last image, we have cosecant theta minus sine of theta all over cotan of theta. Now, once again, you don't have to know all of these. The ones you remembered from secondary school are that secant theta is equal to 1 over cosine, which is equal to cosecant theta over cotan of theta, which is also equal to tan of theta over sine of theta. Of course, the first one is the more useful one, and now you understand why secant theta is 1 over cosine, as opposed to what I was always curious, why is secant theta not defined as 1 over sine of theta? Because after all, should not the complementary parts be associated with the complementary ones? Again, I didn't know the definition. However, now we see that this is a consequence of similar triangles. Finally, let's take the ratio of these sides adjacent to the last angle, and once again we will have the shorter length in the numerator and the hypotenuse in the denominator. So we have that in the first one, sine theta over 1. In the second, we have tan theta over secant theta. In the third, we have 1 over cosecant theta. In the fourth, we have secant theta over cotan plus tan. In the fifth one, we have sec theta minus cosine of theta all over tan of theta. And in the last image, we have cosine theta over cotangent of theta. And once again, in the last one, you should realize this is probably true because you have cosine of theta over cotangent. Cotangent is cos over sine. So dividing cosine by the ratio cos of theta over sine of theta, that leaves you with a sine theta in the numerator. But again, the most important consequence here is that cosecant theta is 1 over sine of theta. It also happens to equal secant theta over tan theta or cotan of theta over cosine, but those are an aside. What you probably remember from secondary school is the first. Cosecant theta is equal to 1 over sine of theta. In summary, applying the idea of similar triangles gives us 5 of the formulas that you should be by now familiar with. And all of these are simply a consequence that we have a number of right-angled triangles, all of which are similar, and these are the immediate consequences. One of the problems, however, is far too often people define tangent of theta as sine over cos or secant of theta as 1 over cosine without looking at the geometric interpretation of that distance. Consequently, you can deduce the other formulas, but you're only deducing the formulas based on algebra. It makes a lot more sense to understand that secant theta is the length of the line that extends along the x-axis from the origin to where the tangent line intersects the x-axis. Once you have that, you have a right-angled triangle, and you can then look at the similar triangles and see that yes, indeed, that length must be 1 over cosine of theta. Thus, if we define sine, cosine, tangent, cotangent, secant, and cosecant as the lengths of these line segments shown here, all relative to a unit circle and a line that forms an angle theta with the positive x-axis, then the Pythagorean theorem automatically yields these 6 formulas, the first three of which you should be familiar with, but the last three of which are just simple consequences of these triangles. You could, if you wanted to, try to prove them from your definitions, and that might be a little bit of fun, but it's a lot easier to derive them from the right angles from the defined distances. And similarly, similar triangles conclude that all of these ratios are equal. Now, once again, you've seen a small number of these ratios in secondary school, but indeed, all of these are the same, and if you were to work them out, again converting everything into, say, just sine and cosine, you will see that they do indeed cancel each other out, giving the results you want. Now, all of these formulas we've seen here today, you could deduce simply using algebra and the rules you learned in secondary school. So, for example, to prove that cosecant theta squared plus secant theta squared is equal to tan theta plus cotan theta all squared, well, let's just replace each of those with the corresponding expressions using sine and cosine. So therefore we have this expression is true if and only if the first expression is true. Let's multiply both sides by sine theta squared cosine theta squared to get that expression there, and we'll also expand out the quadratic. All right, on the left-hand side we have cosine theta plus sine theta each squared, which is equal to 1. And on the right-hand side, notice that we have 2 times sine theta over cosine theta times cosine theta over sine theta, so that's just equal to 2. Now let's expand the right-hand side, and we get that expression there. You may be at a loss here, but wait a second, that's a perfect square on the right-hand side. It's the square of sine of theta squared plus cosine of theta squared, but sine of theta squared plus cosine of theta squared is equal to 1. 1 squared is equal to 1. Therefore, 1 equals 1. Therefore, as in every single step, all we did was apply truths. Therefore, the first statement is true if and only if the last statement is true, and 1 does indeed equal 1. Therefore, cosecant theta squared plus secant theta squared is equal to tan theta plus cotan theta all squared. Here's another formula. This formula was deduced from similar triangles. Let us try to prove that this formula is true using algebra. Well, first of all, the right-hand side is the expression on the left. Let us replace each of those expressions with their corresponding ratio in terms of sines and cosines. Let us now multiply by 1, where 1 specifically is sine theta cos theta over sine theta cos theta. Now, expanding this out, in the numerator, sine theta cancels with sine theta, leaving just cosine of theta. In the denominator, in the first term in the denominator on the right-hand side, the sines cancel and we're left with cosine of theta squared, and in the second term in the sum, the cosines cancel, leaving sine of theta squared. So therefore, this expression is equal to cos of theta over cos of theta squared plus sine of theta squared, but the denominator is equal to 1, and therefore the expression that we started with is equal to cosine of theta. Thus, in this topic, we've introduced some very simple trigonometric concepts and formulas. Thus, given an angle theta, we can define 6 separate lengths: sine theta, cosine theta, tangent, cotangent, secant, and cosecant for that given angle. This collection of lines defines 6 different right-angled triangles, all of which are similar. For each of these 6 right-angled triangles, we get a formula by the application of the Pythagorean theorem. Also, as all the 6 triangles are similar to each other, the ratio of the corresponding sides for a given angle must also be equal. Thus, similar triangles gives us another plethora of formulas. Finally, we concluded by showing that we can deduce all of these formulas using algebra, but it's a lot uglier and it leaves nothing to the imagination and nothing for intuition. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!